Now we look at part B of 2016 HSC Mathematics paper, question 16. Some yabbies are introduced into a small dam. The size of the population y of yabbies can be modeled by the function y equal to 200 over 1 plus 19 times e to the minus half t, where t is the time in months after the yabbies are introduced into the dam. Part 1 shows that the rate of growth of the size of the population is given by this expression, 1900 times e to the minus half t over bracket 1 plus 19 e to the minus half t whole square. Part 2, find the range of the function by justifying your answer. Part 3, show that the rate of growth of the size of the population can be written as y over 400 bracket 200 minus y bracket. And 4, hence find the size of the population when it is growing at its fastest rate. For part I, they are asking us find the rate of the growth of the population. So we have rate means derivative, so we differentiate. Again, I write this in the form of power. So the denominator is written as a negative power. Okay, from here I get dy to dt is equal to 200. This power comes down and the power decreases by minus 1, and I times by the derivative of the expression inside the bracket, which becomes 19 times minus half, 19 times minus half times by e to the minus half t, e to the minus half t. Okay, let's see what does this give us. So dy over dt becomes, if you times 200 by 19 by minus half, and you got minus 1 there, so it becomes positive. So 200 times half is 100 times 19 is 1900. So we considered all the constants which are times together to become 1900, and then we have this expression with the power of minus 1, so it means that we can write it as at the denominator. And this one, keeping its power, we can keep its power as negative, we can keep it at the numerator. Okay, so that is what they asked us to prove. Sorry, I should have decreased the power of that by 1 to minus 2. So that means this goes into the denominator and becomes square. Okay, so you have dy over dt is equal to that as they asked us to show. And in part 2, find the range of the function by justifying your answer. So y is 200 over 1 plus 19 e to the minus half t. As t goes to the infinity, 19 e to the minus half t goes to 0. Because when you have a negative power, the graph of an exponential function, when it has got a negative power, for example, when you have y equal to e to the minus 2x, will be something like that. So it is a decreasing function. And as x goes to the infinity, your y approaches 0. So here we have an exponential function with a negative power, and as the power increases in absolute value, or the value of t increases, it approaches 0. So that bit becomes 0. That means that your y will approach 200 over 1 plus 0, which is 200. Okay, that is one limit for your y. And initially, when time is 0, so because we said this function, a negative function will look like that, which is decreasing with time. If I draw 19 e to the minus half t, that will be something like that. Of course, we are not using a negative time, so it will be like that, decreasing as the time goes. And so that means that initially this has got its maximum value, which is here, which is going basically to be 19. Alright, so this 19. So 1 plus 19 is 20, so when time is 0, y is 200 over 1 plus 19, which becomes 10. Okay, so that will be the minimum value of your y, because here you have, when time is 0, you have the maximum possible value for your denominator, and when the denominator is a maximum, the function is a minimum. So that's the minimum. And here, that's the maximum value that you're going to have, because as this decreases, your denominator decreases, increasing the value of the fraction. And that will be the maximum value. So then you can say that your range y is between 10 and 200. But remember, I cannot put equal to 200 because it will approach 200 and it will not be equal to 200. So that is our range. Part 3, show that the rate of growth of the size of the population can be rewritten as this value. So we got to show that the rate which is given by that, we know that the rate in the previous part we proved is equal to this expression we want to show that this can be rewritten in this form. To do that, we use the expression for y that is what we have for y as a function of t. So what I do here, I switch the place of these two. You know that when you have like 6 equal, or say 2 is equal to 6 on 3, you can switch the place of these two and you still have a correct expression. So I'm switching the place of these two. Similarly here, I can switch the place of y and the denominator. That gives me 1 plus 19 e to the minus half t is equal to 200 over y. Then I take away 1 from both sides and I get 19 e to the minus half t is equal to 200 over y minus 1. But why I'm doing that? Because as you can see here, in the expression for the derivative, I have 19 e to the minus half t everywhere, here and here. And if I can get rid of them and write it in terms of y, then I'm going to achieve this expression. Alright, so then my dy over dt, wherever I've got 19 e to the minus half t, I'm going to replace it with that in this expression. So the only thing here, this one is 100 times 19 e to the minus half t, because this is 19 times 100. So then this is 100 times e to the minus half t, 19 times e to the minus half t, which gives me 200 over y minus 1. In other words, you can write this as 100 times 19 e to the minus half t, and that bit is the same as this expression, and we got 100. Alright, now for the denominator I have 1 plus, now I've got exactly 19 times e to the minus half t, which I'm going to write this 200 over y minus 1. Alright, so that gives me dy over dt is equal to, that 1 and 1 cancels out, becomes 200 over y, and that becomes 100 times 200 over y, and so let's just rewrite this at the top. Okay, so this 1 and minus 1 cancel out. I end up with dy over dt is equal to, the numerator is 100 times 200 over y minus 1 over 200 over y, and but this was squared, so this should be squared. Okay, now we simplify that. Dy over dt is equal to, that becomes squared, for 200 squared is 40,000, and y squared, and this times that becomes 20,000 over y minus 100. Alright, now dy over dt is equal to this, I can treat this big fraction one as a division, and then you know, when you're dividing two fractions, you can write the first one as it is, which is the top, and then times it by the reciprocal of the other fraction. So I just flip this fraction. Okay, so that gives me dy over dt is equal to, if I times that by that, that's 20,000. If I times that by that, becomes 20,000 over 40,000, and that is y squared over y minus 100 y squared over 40,000 dy over dt is equal to 20,000 over 40,000 is half, and y squared over y is just y, minus, divide the top and bottom of this by 100, you get y squared over 100. Okay, so here they have factorized for y over 400, so I do the same, y over 400, and this one, the second one, becomes just y left from that. If I expand that, I get this back. But I should end up with half y here, so y is already here. So I've got 400 here, so it means that I need to put 200 here. If I expand this back, I'm going to get, which is the expression that they wanted us to prove for part 3. So your rate of the change is that much, given in terms of the function itself. And eventually in part 4, they are asking, hence find the size of the population when it is growing at its fastest rate. So basically, first we got to see when the population has got its fastest rate. So we prove that the rate of the population is y over 400, 200 minus y. Okay, I can write this as 1 over 400 times y times 200 minus y. Or maybe even I can expand it, becomes 1 over 400 times y times 200 becomes half y minus 1 over 400 times y is y squared. Okay, so this is a concave down problem. With intercepts y equal to 0 and y equal to 200. Y equal to 0 will make that one 0, y equal to 200 will make that one 0. So basically what it means, if this is my y, and this is dy over dt, okay, so on the vertical axis I'm putting the value of dy over dt, and on the horizontal I'm putting the value of y. So I have one intercept here and one intercept at 200, and it's a concave down, so it's going to be like that. Okay, and they are asking us when the for the value of population when your rate is a maximum. The rate, which is dy over dt, is maximum here, which is basically your vertex, and it is halfway between your intercepts, 100. Okay, so the size of the population is 100. So when y is equal to 100, the rate of change is the maximum. The rate of change is or it's growing at its fastest rate. Okay, that answers the question to 4th. Thank you.